This lesson on data representation is looking at how we represent sound in a computer. A computer that obviously can only store numbers. What you're seeing here is an example of an analog wave. You can see it's infinite in resolution. There's no pixelation, as you like. There's no sort of quantifiable sort of blocks in it. It's just perfect. It's a natural wave. It hasn't been quantized in any way. You'll understand what I'm talking about in a moment. So how do we take that perfect infinite wave and convert it into something quantifiable and store it on a computer? Well, it's all down to sample rates. Let me show you. Here is a wave, and here are some time intervals, and here is values, amplitude in this case. So this is time. So if I wanted to represent that wave in a computer, all I have to do is pick a sample rate, an amount of times per second I'm going to look at my wave, and then just take down the value of the wave at each one of those time intervals. For example, here, here, here. And if you notice, rather than a perfect, lovely, beautiful analog curve, we have a rather less pretty, jagged, artificial curve. That's why when people say, "Oh, if you want to listen to music, you've got to listen to it on a record. CDs don't do it justice." Well, that's because CDs are a digital file format. They've had to go through this form of analog to digital conversion. Flies in here. Okay, so let's look further at this topic. Right. So yes, obviously then, the more times you sample an analog wave, the more values you're going to store, and therefore the larger your file size is going to be. However, the smoother your digital wave will be, and so the more pure it will be, the more lifelike, the more analogous to the analog wave it will be. So you've got a trade-off there. Do you go for more samples, get a better quality sound, and have very large file sizes, or do you go for less samples and have a not so good sound quality but smaller file size? And it all depends upon the application. For example, a telephone doesn't require a very large, it doesn't require good quality sound. You don't listen to Beethoven over the telephone. And that is why at any one time, it's a little bit of a silly fact, at any one time, the entire telephone conversations held in the UK can fit very easily down a single optical fibre. That is because A, optical fibres can hold an awful lot of bandwidth, but B, a telephone call data is very, very small. Just as a matter of interest, how does a microphone work? How does a microphone convert analog signals into digital signals that a computer can understand? Well, it's all down to magnets and coils, just like an electric motor. If you look at your big bass, big sort of subwoofer, it's got a piece of paper, that's the bass bin, but that piece of paper is connected to a magnetic coil, a magnet. That magnet is suspended inside a coil, And when this is a speaker I'm talking about, but speakers and microphones are exactly the same thing, but just work in reverse. So when your computer wants to play a sound, it vibrates, it sends a signal to the coil. The coil then agitates the magnet, which then moves the piece of paper on your bass bin, which forces a sound. Well, it creates sound because you're compressing air. You're transmitting that energy via air. That's why you can't hear anything in space, because there's no air in which to create the waves. That's a bit of a sort of silly aside. Right then, here we go. Have a look at this example. You've got a sort of a nice analog sort of sinusoidal wave, and well, each sample time, you need to capture the value of the wave and put into that table there. Then obviously convert it to binary, and that's basically how sound is stored in a computer. There it is. You can see that the digital version is not as nice, not as clear, not as perfect as the analog wave, which is why a CD or an MP3 or anything digitized will never ever be as good as the real thing. Interestingly, MP3 files considerably smaller than CD files. That's because when they were designing MP3, they realized that they were going to be stored on small portable devices and played merely as a distraction more than anything else. You don't sit down with your MP3 player and in a sort of a darkened room with the curtains drawn and big headphones on and want to listen to perfect representations of your music. You basically walking down the street with all the bus noises and people walking past and cars and the wind. So that is why they realised that MP3 files don't actually have to be that good a quality. It's better if they are smaller and can fit on more mobile devices. So key vocab here then. ADC, analog to digital converter. Converts an analog signal to an equivalent-ish digital signal. DAC is the opposite, digital to analog converter. PCM, pulse code modulation. It's just a process for coding sampled analog signals. And PAM, pulse amplitude modulation. You don't really need to know that in GCSE. Right, a little bit more of a real example now. This is a signal that has been quantized or digitized. It's a more usual signal and rather than a perfect sinusoidal wave, and you can see what kind of resultant digital output you get. Yes, not as nice as the real thing. Sample rate. The number of samples taken per second. A hertz, H-E-R-T-Z, HZ, is a sample per second, one sample per second. So 44 kilohertz is 44,000 samples per second. A sample, remember, is what is when you record the value of a wave at a given time. This is one sample because you take the value there. You'd sample a wave there as well, and there, then there, then there, then there. So the more samples you take over a period of time, you obviously get a better representation of the sound wave, but you also get more values to store, so a larger file. Right. So how often do you sample then? Well, there's this guy called Nyquist that came up with a theory. He said you should always sample at a frequency twice the rate of the highest frequency of the sample signal. So if I have a look at this signal here, that wave is over 1 second. If you then sample it, well, actually you can do this as a task. Sample that wave twice a second and see what kind of a wave you get. Then sample it 4 times a second and see what kind of a wave you get. Can you see that you have Nyquist's theory of having twice as many samples as the highest frequency works? Because if you do it 2 Hertz, the wave makes no sense. It's practically 0. But you have to double that and sample it 4 times a second in this particular example in order to get any kind of realistic representation of that sound. So, a couple of other things here then. Resolution, how many bits are assigned to each sample. That is, again, like we talked about before with bitmaps, how large a number are you going to store for every sample? You can store, 8, 16, 32 bits for every sample if you wanted to, and you can find out how a CD samples things and whether it's a 16-bit or a 32-bit number it samples, the resolution. Obviously, a larger number of bits means the larger number you can have, and therefore a greater accuracy you can have for the value of that sample. Sampling rate, as we know, is the regularity of how many times you sample per second. Common file formats, .wav, uncompressed, Windows Audio, I think it stands for. .mp3, that is encoded and compressed. Like I told you, they designed it to go on mobile devices and be played sort of fairly indiscriminately. It's got 20 Hertz, it can only handle 20 to 20 kilohertz, because what they did was they realized that the human ear can only detect those frequencies, and therefore it only samples to those values. What does that mean? Well, if the human ear can only hear up to this amplitude, then what MP3 does is it slices it, so chops these bits off, doesn't bother recording them. So what you get can be a fairly distorted, unrealistic sound. You've got to remember, we're talking purists here. This is the difference between watching the band live and listening to on a little MP3 player. But what you do get with an MP3 file is a lot smaller file size. CD quality is better. It's a 16-bit sampling resolution at a rate of 44 kilobits per second across 2 channels, meaning the left channel and the right channel. So how do we calculate file sizes? Well, 16 bits, a sampling rate of 44 kilobits per second over 2 channels. Well, that's 16 multiplied by 44,000 bits, multiplied by 2 channels, multiplied by 180. Now, where did that 180 come from? Well, in this particular example, we're looking at a 3-minute track. 3 minutes is 180 seconds. Divide that by 8 gives you bytes. Divide it by 1024 gives you kilobytes. Divide that by 1024 gives you megabytes. So you can see here a 16-bit resolution CD quality sample at 44 kilobits per second over 2 channels. A 3-minute track will produce a 30.2 megabyte file. Okay, so what is the file size of a 4.5-minute track stored on compact discs in megabytes? And again, a 6 megabyte track. 6-minute track. Okay then. One more thing. MIDI interface. Basically, you store the sample and call upon those samples rather than represent the sound wave. You don't need to know about this in GCSE. That's maybe something you might want to look at in your own time. Now you will see this though, this is what I would like you to complete, and I shall put this onto the slides for you to complete now.